So now we're going to talk about windings. And so I'm going to discuss windings with regard to winding functions and turns functions, and then we're going to look at different windings and how they affect the harmonics. And so we can then look at different coefficients, factors to account for different harmonic effects. And this is really important because a lot of machines you can end up with a lot of torque ripple if you're designing it. And so to understanding how windings affect the harmonics within the air gap is really important if you want to design an electric machine, or if you want to understand in more detail how the electric machine works. So I just thought I'd just do a little recall. So and so if we have a three-phase winding in which each winding is located at 120 degrees apart. So then we could have an MMF for the three different windings, where NA is the winding function. And so if we assume that the winding function is cosine, where NA is winding function. I'll upload a background document on winding functions and turn functions for those of you that didn't take the prerequisite class. And then IA is a phase current, and P is the number of poles. So if we have MMF related to the A phase winding, and then we have MMF related to the B phase winding. So N sub F would be some magnitude, some number of turns. So this B phase is phase shifted by 120 degrees. And then we have a third, which is also phase shifted with respect to the other two by 120 degrees. So this describes the distribution, the winding function describes the distribution of the physical location of the wires. So now, of the stator conductors. So now, so if we have these three winding functions and they have a certain current going through them, then it turns out that if we then choose these currents to also be phase shifted by 120 degrees, then we can create a traveling magnetic field. So if IA is chosen to be cosine omega ET, where that omega E would be electrical frequency, which would be related to the number of poles, and then cosine omega E T minus 120 degrees, and then IC is cosine omega E T plus 120 degrees. So each of the, so that this, we're now, so we have the first term here is the C winding function that shows you the distribution of the wires in the machine. So that ideally would be cosine, and then we apply a current that is sinusoidal into the winding, and then we do that for the 3 phases. Then we get a magnetic field in the air gap, and so the summation of these 3 results in something kind of magical happening, that we create a traveling magnetic field. So each of these MMFs are present in the air gap, adding up and expanding terms. One obtains, so we have MMF is equal to MMF due to phase A plus MMF due to phase B plus MMF due to phase C. And so if you do the math, which I will skip, but I'll show a simulation on the computer, we get this out here. So this is different to the fit terms in here, because it's creating a traveling field. If you recall from your electromagnetics with wave propagation, so this results as time goes by that the field is traveling around the air gap, whereas these fields are just going up and down in magnitude, but they're not traveling. But when we add the 3 up, it creates a traveling field. And so that's the key ingredient. So traveling field created from 3 stationary oscillating fields. So let's just I like showing this video, so I never get tired of looking at it, so hopefully I can get this to work. So so this is the 3 phases, and so this would be from 0 to 2 pi here. So this would be the winding distribution, okay? Creates this waveform, and then we apply a current into it that would then change the magnitude. And so you can see that they are oscillating up and down, but that's not going to be useful for creating rotation. But when you sum them up, it creates this traveling field, and that's it's really quite clever. And so that's what we want to create. But now what we're going to talk about is that we cannot easily get a perfect sinusoid. So we're going to look at how to create different waveforms to try to approximate a sinusoid, and then we'll also look at different fractional slot winding types that use higher harmonics to interact with the magnetic rotor. One thing to note about that simulation is that when we looked at each individual MMF distribution due to each individual phase, the pole number is the same when you sum them up. It's still P over 2. So when you sum up these individual phases, you will get the same, the number of pole pairs doesn't change. Okay, just keep that in mind. Okay, so now let's just talk about winding functions and turns functions, and I'm going to so I talked about them and how we derived them previously, and I'll give you a handout on it as well if you haven't taken the prerequisite. So I'll just review the winding function, turns function for a 6-slot machine design first. Winding function and turns function. I will I can do this. I will probably cut this part. I will upload, I'll write down the textbook related to this material on the video. I don't have that on me right now because I know some of you like that. Okay, so now winding function and turns functions. So let's consider a simple winding first. So consider a winding such as shown below. So if we now I'm drawing this one, but I should have practiced before the lecture. But after this, there's a handout that I gave you that we can use, and that was created in JMAG. So this is supposed to be 6 slots, and we now on here we'll assume that the rotor has 2 poles, and I'm not going to draw the rotor after this, but we'll just leave the rotor out. But you can assume that there would be some material there, otherwise the winding distribution would not be correct because it would go into a lot of air. So there has to be something in here, but just for simplicity, for the later discussion, I won't put the rotor in there. But just keep in mind that the analysis has to have really a rotor in there, otherwise it would not give the right results. So we could say that we could have an A winding here, phase A. So this is minus A, and this is plus A. Okay, so so this is if you look at the winding, then the wire is going in this slot, and so it's going to create a field coming up, right? And similarly, if you do your right hand rule, it's going to create a flux going up. So then we could draw a flux vector for phase A that points in the up direction. So because again, this would create a magnetic field going up if you just think about the coil, right? If you have this like this, this is going to create a field that goes up. So that's what we have, but we've got magnetic material in here to make the field flow much easier. Okay, so then we've got to have 2 other phases. So then we put in a B phase here and a C phase here, and so then the C phase and the, I better write that, minus C plus C plus B minus B. So now these are, if you look, these are 90 degrees phase shift, 120 degrees phase shifted, so with respect to the A. So the C would be down, the flux created by the C winding, if energized, would be down like this, and then the B winding would create a flux vector in this direction, like so. So hopefully you can see that, visualize those three. So these you can think of as the flux direction. So we'll assume that there's n. So this is drawn as just a circle going in, but there could be n conductors going in there, a lot of strands of wire going in there. So we'll assume that there are n conductors in each tooth. Okay. So now let's look at the winding function and turns function. The turns function for each phase is so remember that the turns function gives the physical location of the conductors. So for the A phase, then if we look here, if we define this as this here is 0 degrees, and we move around, then the wire here is going into the page. So there's n wires going into the page, and then 180 degrees around, there's n wires coming out of the page. So then we can draw the winding function for the A phase like this. So this would be minus n. Okay? And then the B, so did I say winding function? The turns function. This is the turns function. And then the B turns function is starts by coming out of the page at 60 degrees and then going back in 180 degrees later. And so it's going coming out, so it's plus. So that, again, this is just giving the physical location of the conductors. So we have it coming out and then going back across. Like so. So this would be NB. So this would be at 60 degrees, and this is 240 degrees. This should be a straight line here. And then we have the C turns function. And so that starts at 120 degrees going into the page, and then at minus 60 or 300 comes out of the page. So we have 120, which would be around here. looks something like that. So this is 120. Okay. So that's the turns function. That gives the physical locations of the wires. Now there's a couple of terms here that we should use. So the distance between one slot to the next, that's usually often called the slot pitch or slot span. So let me put it on this side. So this distance, this can be written in terms of distance or angle. So between one slot and the next, that's the slot pitch. And so in this case, so the slot pitch, slot span, it's the electrical angle from center of one slot to center of adjacent slot. Okay, and then we also have coil pitch. The coil pitch, also called the coil span. So in this example, the coil pitch is 3 slots. So for the phase A, it's from the first slot to the 4th slot, right? So it's going across 3 teeth. So these are slots and these are teeth. Slot, teeth, slot, teeth. So it's equal to the number of slots spanned by each coil in electrical degrees, or number of slots. So you can define in terms of the electrical degrees or the number of slots. So in this case, it's 3 slots. Okay, so this would be 180 degrees electrical. Okay, so with those definitions, we'll come back to those. So let's now look at this turns function again. So we have the turns function here, and then the winding function can be determined from the turns function by taking subtracting the average of the turns function. So the winding function, which actually I'll put this as NC here for number of conductors in each tooth, because it's a bit confusing because the winding function is defined as capital N. So the winding function is equal to the turns function minus the average of the turns function. And we derived this in the previous class, and I'll upload a document that reviews this material. So then with this definition, then we can look at the three turns functions for the three phases and determine the winding function. So for the A, B, and C, we just have to subtract the average of the turns function. So what is the average of this turns function going to be? N over 2, right? So you can see this is N over 2. So then, so in this case, it's going to be added on there because it's all negative. Because negative plus negative equals a negative. Negative equals a positive. So we have that the winding function for the A phase looks like this. So this would be N over 2 minus N over 2, 180, 360. And then for the B and the C, we can also draw up the winding function. And so the B will look something like this. And then the C will look something like this. Where this would be 150 degrees and this is 60 degrees here, and then this is 120, right? So they're phase shifted by 120 degrees. Now if you look at those waveforms, they're square waves. But we would like, at the beginning we talked about having sinusoidal waves. So you can see that there is a fundamental here that we could put on here, like so. And so then this winding is not going to create an ideal set of three-phase windings field distribution. It's going to introduce lots of additional harmonics, because in this analysis we can see that it creates this square wave type of waveform. And then we could, to get the complete field distribution, we would need to add these three up. But I won't do that just yet. We'll just look at the winding distribution for one phase at the moment, because we can actually learn quite a lot from doing that. Okay. So there's lots of harmonics present, and we'll look at those in a minute. So we'll go. We're going to study this in more detail in a minute. But before I do that, let's just think about this distribution a little bit more. Any questions on that? Okay. So in this arrangement here, we just had the one conductor going into that slot. So you could picture it as being a block. Now in finite element analysis, you can't But you can't. There would, the slot would not look like this, and not a real one. But for now, we're just drawing it simplistically. But just an aside, in finite element analysis, you can't. Usually what you do is you define this whole area as being a current, and then you select a current density for this region, because and you have to also think about the fill factor, because in reality the wires is not nice and perfect like that. It's got if it's circular, it's going to have spaces between the conductors, and so it's not all going to be conductive material. There's going to be lots of air spaces, and the wires also have some coating on them. So then there's a fill factor that you have to account for. You have to assume that they're not all going to be, it's not all going to be conductor. So then the current, the density, the current over the area of the slot needs to account for the fill factor. And so those things need to be looked at when modeling. You don't usually model all of the conductors individually because that would result in an extremely long simulation calculation, and it doesn't add that much to the model. So, but in this example here, we had one conductor going into each slot. So this is a single layer winding. If we had two conductors in the slot, then it would be it would not be a single layer. It would be a two layer. And we'll look at what benefits there are of having multiple layers in a bit. So then in this example here, we had and the number of slots being 6. So if I define the number of slots as Q, then this is number of slots. That's 6. And then in this example, we had two poles. That's in other textbooks and classes and other lives, P is pole pairs. In this discussion here, it's poles. I'll try to not say pole pairs. And then M is the number of phases. So in all of this discussion, in this class, it's just going to be 3 phases. So then with these 3 pieces of information, we can define the number of slots per pole per phase, which is something that people talk about quite a bit in machines. So, number of slots per pole per phase. So that we can call Q, lowercase q. So number of slots per pole per phase. So in this example, we have 6 slots. We have 3 phases and 2 poles. So we have 1 slot per pole per phase. So we'll look at what the benefit is of having a higher number of slots per pole per phase, and also what happens if we have a lower number of slots per pole per phase. You could have less than 1, or you can have more than 1. So then if Q is a integer, it's called an integer slot winding if Q is not an integer. It's called fractional slot winding. Okay, so in this winding we could also draw up a winding diagram, a winding layout. So winding layout. So in this example we have 6 slots. 1, 2, 3, 4, 5, 6. So if we, for A phase, now we can number these as 1, 2, 3, 4, 5, 6. And so then the A winding is going into A and out into 1 and out of 4. So then it's coming down here and then coming back out here like that. And so these two have to be connected, and so they'd be connected by end windings. So you could think of this as the cross section of the machine in the axial direction. And so this then shows the wires coming out of the sides of the machine. It would, unless the machine was really narrow, the end windings would not be, would be a relatively small percentage of the total axial length. But in this case, they're exaggerated. So we could draw something like this. So that would be A. Let me see. I thought I had lots of colors, but I realized they're all the same color, just different cap colors. So I can't use a different color. So now B is going out of slot 2 and then coming in slot 5. So then we have it coming out here and going in here like that. So then this is then connected around here. Like so. And then C is where's C? C is going in of 3 and out of 6. So it's going in here and out here. So we could draw that also. So it could look something like this. And so this is one possible winding configuration. And we'll talk about, so this is an overlapping lap winding. So we'll talk about different windings as well. B and C. Okay.